Hello, in this video we are going to see a simulation of indifferent curves and budget constraints. In the previous video we have seen that if this is the utility function that has this graph and this is the budget constraint that is represented by this magenta line, then we get the maximum utility subjected to this budget constraint in this point, phi 5. Okay, we have also seen that this is a representation of the budget constraint in 2 dimensions, and if we want to see it in 3 dimensions, it's going to be a vertical plane, this one. So if you evaluate the utility function in this solution, the optimal solution, phi and phi, so you have phi here and phi here, you evaluate this and you get 2.5, which is, we can see it here, this here, 2.5, between 0 and 5. Okay, what we are going to see in this video is what happens when you change the values. Let's say you change the value of a, then you change this exponent. You can see here that the sum of the exponent is 1. If you increase the budget or if you change the prices, and we are going to see a brief interpretation of this, which is the gradient that is expressed as the partial derivative, this and this, that is going to be useful when in a future video we show the Lagrange method. Okay, but let's go step by step. So first thing, here we use good 1, good 2. In the previous video we have used printers of good 1 and cutter as good 2, and if you use labor as good 1 and capital as G2, good 2, then you get the Cobb-Douglas function, where A is the total factor productivity, and this is going to be useful in future videos to analyze the economy in the long run to understand the Solow model and time series. Okay, but let's go step by step. First of all, why this function has this shape? Well, if we use a new figure and here we write x equal, we are going to take 100 values from 1 to 100, and then if we plot that, okay, if we plot that, then plot x versus y, then you get this curve, which is exactly the square. You could have written, instead of this, you could have written here E equal to square x, and then you can see we are going to erase this, and then if you plot it again, you will get exactly what we got before. So this here, x power 0.5 is the same as square x, which you have this shape. Okay, so if here you take the point 0, 0, then you will get a 0 here, which is this point here. Now, if you take for G2 the value 20, then 20 square is a constant, this is a constant, so what you get is something like x power 0.5, so you get this, which is square. So that's why for the value 20, when good 2 is 20 constant, then you get this shape. When good 1 moves vary, then you get this shape here, which is very similar to this shape here. Similarly, if G1 is constant, let's say to the value 20, then from here to here all of this is constant, and then what you get is G2 variable, which is this part here that you get when G good 2 varies. Now, if the budget vary, let's start from the beginning and let's see the vertical plane here. If you get double budget, then this line will move from 20 to 20, and then you will see the plane passing through 20, 20 here, and this value will increase because this wall goes toward this corner. Let's see it. So if we, and the solution instead of being 5, 5 is going to be 10, 10. So if we increase this to 20, then it is 20, 20, then the wall pass through 20, 20, and then the solution is 10, 10, and then when you evaluate this 10, 10 here, you get 5, which is this value 5 here, okay, 5. Okay, when the price of this wood is double, we have seen before that this point goes here because you can buy half the quantity of wood that you buy before, so you get this, okay? If this price of the wood 2 is, let's say, 3, then you will buy the third part of the quantity, so you divide it in 3, so it would be about here. So the magenta will go like this, the magenta line, okay? So 3, then you have this. Now let's start from scratch. If you duplicate one important thing, these are the indifferent curves, meaning that the function take higher values as you approach this corner. We have seen this in the previous video. So if you change this, these indifferent curves will not change because this function doesn't change. The only thing that happens is that this line goes up parallel. So when we did that, you see that the indifferent curve didn't change, only this changed. Now, if, let's go to the beginning, if you change the value of A, that in Cobb-Douglas is the total factor productivity, then see what happened. Here the optimum was 5 and 5, and it was 2.5 the utility, the maximum utility, and you can see that this 2.5 is represented by this yellow optimum indifferent curve, and you can see that it is between the label 2 here and 3, so that's why it's 2.5. Now if we increase this, we duplicate the value of A, then the maximum utility is going to be 5, and then this yellow line will be not between 2 and 3, but between 4 and 6, double. And this will go up. So let's see it. If we change, we duplicate, then this goes up, and here the value, the maximum is 5, and the optimal solution is still 5 and 5, but when you substitute 5 and 5 here, you get the value 5, which is this yellow optimum indifferent curve, and you can see that it is between 4 and 6. So for every indifferent curves, now you duplicate, because here you duplicate the value of the function. Okay, and finally a little bit of comment about this, which is the gradient that you get mathematically with the partial derivatives. So you take the partial derivative of utility with respect to good 1. So what you do is to take good 2 as constant, and then you vary only good 1, and then you get this, and this is the normal concept of derivative in one dimension. And here you do the opposite. Good 1 is constant, and you vary only good 2, and then you get these two derivative. So this value of the derivative that you can see here, which is from 5 to 10, 5 is 1 and the other one is also 5. So this is 5, you can see from 6 to 10, 5 and 5. Then this 5, with these two partial derivatives, you get the gradient, which is this. But if you forget the mathematical part, the gradient tells you two things. One thing is, in this point, it tells you in which direction, which is toward this corner, in which direction this function grows with maximum slope, which intuitively you can see that is from this corner toward that corner. Here is from this corner toward this point. And the magnitude of this gradient tells you intuitively how steep you are, let's say, climbing this hill. So if you go back to 5, then you see that the partial derivative now is 2.5 and 2.5, and this 2.5 and 2.5 lead you to a gradient which is smaller than before, because you are growing in that direction but with lower slope. So if you increase this, then you get more slope in the derivative, because both grow, you see here and you see here, and also the gradient is bigger. Now if you change this, let's say to the value 2, then the optimum is not in 5, it is in 5 a little bit more than 2. So what we are going to see in the Lagrange method in future videos is that you find the optimum in a point in which the indifferent curves is tangent to the budget constraint. And in this point, this is the gradient, and we are going to see in future videos that the partial derivative of good 1 is smaller than the partial derivative respect to the good 2, and we will see that the gradient of the function has the same direction as the gradient of the budget constraint. We are going to see this in detail when we see the Lagrange method. Okay, that's it. In the previous video we are going to see very briefly the relationship between this and the indifferent curve and the constraint that we use when we analyze the medium run, and the strategy that the central bank used to target inflation and GDP. Okay, thanks for watching, and see you in the next video.